Now that we've learned about network models, layers, and addressing, let's move on to the next topic, Ethernet LANs. In this section, we'll delve into basic Ethernet operations, as well as cover repeater, hub, and bridge operation, and Ethernet switch operation. Today's complex networks are built using many different network devices. The names of these devices might be familiar to you and include routers, switches, and more. But to understand what these devices do and how they work, we first need to take a look back in time. Networks have grown at a pace not anticipated even a few years ago. Worldwide, more than 1.6 billion PCs were in use by the end of 2011. New network devices have been developed along the way to address specific problems resulting from this growth. To understand the different network devices used in today's networks, it's helpful to understand the predecessors to those devices. To gain that understanding, we're going to take a look at the history of a fictional company, call it Acme Company, from its roots in someone's garage to that of a multinational company. When Acme Company was established in the mid-1980s, the company had only a few PCs. Their networking needs were pretty simple. They needed to share documents and spreadsheets as well as a single printer. In networking terms, PCs and printers are known as end-user devices, hosts, or just devices. As we mentioned in Section 1, a geographically limited network is called a local area network or LAN. To create a LAN, end-user devices must be connected, either physically with cables or wirelessly. A LAN also requires a set of rules controlling communication on that connection. And the most common set of rules is called Ethernet, a LAN network technology developed in the 1970s. Ethernet is a set of standards that define rules, such as frame format, as well as how computers communicate with each other over a single wire shared by all devices on the network. These rules give any new device attached to the wire the ability to communicate with any other attached device. Although Ethernet technology has evolved considerably since it was first implemented, the fundamental operations remain the same. Ethernet standards include a number of components. First, there are the physical layer characteristics. In other words, what does the physical layer, or layer 1, consist of? Next, there is the protocol that controls access to the network. And finally, there is the frame format. We'll cover all of these components. Ethernet was originally deployed with multiple computers connected to the same physical wire or cable. This physical network topology or layout is called a shared bus, meaning that when one computer transmits data, all other devices on the shared bus or network segment receive it. If there is a break in the cable, devices can no longer communicate. By the way, the term network segment means different things to different people. In this course, the term network segment, or simply segment, refers to the group of network devices that compete with each other for access to the wire. To refer to the actual cable or wire used to connect network devices together, we'll use the term physical cable segment. Let's look at the functionality of network segments in more detail. How do end-user devices connect to the network segment? And because multiple end-user devices can connect to the same network segment, how do devices know when it is their turn to send data? Finally, because all devices receive the data, how does a device know that the data is intended for that device? We'll answer all three of these questions in this section. To connect to the network segment, a device uses a Network Interface Controller, or NIC, and Ethernet cabling, or a wireless NIC. Click the link on screen if you would like to learn more about NICs, or click the Continue button to continue with this topic. A Network Interface Controller, or CARD, is a computer hardware component installed in a computer or printer so that it can be connected to a network. The terms NIC, Network Adapter, Network Card, and LAN Adapter are used interchangeably. In the 1980s, a NIC was an expansion card that plugged into a computer bus. Today, most computers have a NIC built into the motherboard, and a separate card is not required unless you need connections to multiple networks. NICs on personal computers today commonly use either Ethernet cabling or a wireless connection. A wireless NIC with a USB interface can easily be added to almost any computer. Ethernet operates at layers 1 and 2, which you might remember are the physical layer and the data link layer. Both of these layers are implemented on the NIC. The Ethernet physical layer defines such things as the connection speed and the type of cabling. Both have evolved over time and are discussed later in this section. The second component we mentioned previously was the protocol controlling access to the network or wire. That is, how do devices know when it is their turn to send data? Access to the physical wire or segment is controlled by a Media Access Control or MAC protocol. Ethernet in particular uses Carrier Sense Multiple Access with Collision Detection or CSMA-CD as its MAC protocol. Other MAC protocols exist for other technologies. To understand CSMA-CD operation, think of a group of people having a conversation. As we discussed in Section 1 on protocols, in general, human conversations work only when one person talks at a time. That way, everyone in the group can hear and understand what is being said. The same is true of computer networks, and in the case of Ethernet LANs, the CSMA-CD protocol regulates the conversation. If a device has data to transmit, it listens on the wire to see if any other device is transmitting. If the wire is idle, the device sends the data. All other devices on the segment receive the transmission. Now, what's important to remember about the CSMA-CD protocol is that it allows a network device to either transmit data or receive data, but not do both simultaneously. This type of system is known as half-duplex communication. A half-duplex system provides for communication in both directions, but only one direction at a time. Half-duplex data transmission is similar to using a walkie-talkie. If you want to talk, you need to press the talk or transmit button. While you're talking, the other person cannot transmit to you. Full duplex communication, on the other hand, sends and receives data at the same time. We discuss full duplex communication in more detail later in this section. On a network using half-duplex communication, when one device on a network segment is transmitting data, other devices cannot transmit data. Any device that needs to send data must wait until the line is clear. While all computers listen to the wire first to make sure the wire is idle before they send data, sometimes data collisions do occur. Let's return to our conversation analogy to see how this problem can happen. If there is a lull in the conversation and two people try to say something at the same time, others in the group might not understand what either person is saying. At this point, one person stops for a moment and allows the other person to resume speaking. The same thing can happen if two devices listen to the wire, believe it is idle, and try to transmit data at the same time. This condition is known as a collision, and this is where collision detection, the CD part of CSMA-CD, comes into play. When a collision occurs, both transmitting devices stop transmitting, wait a random amount of time, and attempt to transmit again when the wire is idle. Click the link on screen to learn more about how collision detection works, or click the Continue button to continue with this topic. In half-duplex Ethernet networks, after a device transmits data, it listens to the network and expects to hear the same data in the exact same pattern. If the device hears a different pattern, it assumes a collision has taken place. When a collision occurs, both transmitting devices send a jam signal. This jam signal indicates to all other devices on the segment that there has been a collision and they should discard the partial frame they have received. The jam signal also causes all transmitters to set a random retransmission timer, reducing the probability of a collision when the first retry is attempted. When each device's timer expires, they begin the transmission process again, hopefully at different times. If another collision occurs, the timers are set to randomly longer periods of time until the frame is successfully transmitted. A network segment is also known as a collision domain. With CSMA-CD, as more devices are added to the network segment or collision domain, more collisions occur, degrading overall network performance. The increasing frequency of collisions was a major obstacle in the development of networks. We'll see shortly how network designers overcame this obstacle. Now let's move on to the third question posed earlier. How do devices know which data is intended for them? Let's begin by looking at how data is encapsulated. When a device needs to send data, the NIC encapsulates it into an Ethernet frame. The NIC prefaces each frame with a preamble and start delimiter. This specific 8-byte sequence, shown on screen, allows receiving devices to recognize the start of a new frame. The preamble and start delimiter are not considered part of the Ethernet frame itself. Ethernet standards define the Layer 2 frame format, which has evolved over time. You might hear people use the terms Ethernet and 802.3 together or separately. Click the link on screen to learn more about Ethernet evolution and the term 802.3, or click the Continue button to continue with this topic. Ethernet is the most popular and most widely deployed network technology in the world. You might have also heard the term 802.3 used in reference to Ethernet. The origin of that term actually goes back many years and warrants an explanation. Historically, the term Ethernet actually referred to a family of technologies that included LANs and Metropolitan Access Networks, or MANs. Recently, Ethernet has been implemented as a Wide Area Network, or WAN, technology as well. Ethernet was originally developed by Xerox and then standardized by DEC, Intel, and Xerox. This standardized version is referred to as Ethernet version 2. Soon after, the Institute of Electrical and Electronics Engineers, or IEEE, created a committee to standardize network technologies. They named the committee 802 because it was formed in February 1980. Since then, different subcommittees have worked on different aspects of networking. Each subcommittee is assigned a unique number that is appended to the working group number. For example, the 802.3 group standardized the operation of CSMA-CD. The 802 committee was also interested in standardizing different networking technologies, such as token ring, which is 802.5, as well as a method of supporting alternative Layer 3 protocols, which is 802.2. Many people are familiar with the term 802.11, which defines wireless standards. Because the IEEE standard differed slightly from the DEC Intel Xerox standard, the frame formats also differ slightly, as shown on screen. The 802.3 frame format includes a logical link control, or LLC portion, which allows Layer 3 protocols, other than IP, access to the wire. Examples of other non-IP protocols include Apple Computer's AppleTalk and Novell Network's IPX, the discussions of which are outside the scope of this course. While Ethernet and 802.3 differ slightly in their terminology and their frame format, their media access control, or MAC protocols, are virtually identical. Today, the term Ethernet refers generically to both sets of Ethernet standards. The Ethernet frame includes the destination Layer 2 address of the device receiving the data, as well as a source Layer 2 address of the device sending the data. Each NIC has a unique Layer 2 address that is assigned by its manufacturer. The manufacturer burns this address into a programmable read-only memory, or PROM chip, on the NIC. The NIC uses this address as the source address in a frame. For the destination address, it uses the address that is burned into the NIC on the receiving device. A Layer 2 address is also known as a hardware address, a physical address, or a MAC address. In this course, we will use the term MAC address for a Layer 2 address. Use your mouse to learn about the other fields in the Ethernet frame. Click the Continue button when you are ready to move on. The destination address is the Layer 2 or MAC address of the device that will receive the frame. The source address is the Layer 2 or MAC address of the device that is sending the frame. The type field identifies which Layer 3 protocol is being transported in the Ethernet frame. Protocol types include IP, AppleTalk, IPX, or something else entirely. This field is the only one that differs between the Ethernet 2 and 802.3 frame formats. In an 802.3 frame, this field indicates the length of the frame. The data field contains the original data created by an application, as well as the headers that have been added by each layer during the encapsulation process. Note that at Layer 2, we do not deal with any of the information added by the other layers but treat it all as one piece of data. The checksum field includes a cyclic redundancy check, or CRC, which is a method of checking for errors in data that has been transmitted on a communications link. Let's take a closer look at MAC addresses and how they are used by a device. A MAC address is a 48-bit or 6-byte address that uniquely identifies a device's NIC. We'll cover bits and bytes in detail in Section 4, but for now, understand that a byte is comprised of 8 bits of data. So 6 bytes is the same as 48 bits. Take a look at the MAC address on screen. MAC addresses are typically expressed in hexadecimal format, a numbering system that uses 0 through 9, but then also represents numbers greater than 9 using the letters A through F. We'll discuss this and other numbering systems in Section 4. Each digit represents 4 bits, so 1 byte, which is 8 bits, is represented by 2 digits. For example, in this MAC address, 00 is the first byte, 90 is the second byte, and 69 is the third byte. The bytes in MAC addresses are displayed using dashes, colons, or dotted decimal format as shown on screen. Breaking down MAC addresses further, each is broken down into 2 components. The first 3 bytes of the MAC address comprise the organizationally unique identifier, or OUI, that every Ethernet equipment manufacturer is assigned by the Institute of Electrical and Electronics Engineers, or IEEE. In our example, we've used 00, 90, 69, which is the Juniper Networks OUI. The manufacturer then uses the remaining 3 bytes to assign a unique number to the NIC. When the NIC is ready to send data, it adds the destination and source MAC addresses into the frame and transmits it on the segment. To keep our animation simple right now, we'll just show the destination address on the frame, designated with the letters DA. Because Ethernet is a shared medium, every device on the segment receives every frame and compares the frame's destination MAC address with its own MAC address. If the destination MAC address does not match, the NIC discards the frame. If the destination MAC address matches, the NIC processes the frame. First, the NIC compares the cyclic redundancy check, or CRC checksum, on the frame received with the CRC that was generated by the sending computer. Next, if the frame length is the same and the CRCs match, the NIC examines the frame type to determine the upper layer protocol. Then it strips off the Ethernet frame and forwards the data to the appropriate upper layer protocol. Before we close out the subject of MAC addresses, there's one more detail we need to cover. So far, we've been talking about MAC addresses that are unique to both the sending and destination devices. That is, when one device sends data to another device, the destination MAC address is a unique MAC address, which is also known as an individual or unicast address. But what if one device is sending data to multiple devices? This scenario requires MAC addresses as well, but of a different sort. If a device needs to send the same data to every device on the network, it uses a broadcast destination MAC address. This special address used for broadcasting is shown on screen. If a device needs to send the same data to a group of devices on the same network, it must use a group address or multicast MAC address. Multicast addresses always have the first bit of the first byte set to 1. Unicast, broadcast, and multicast addresses are all hexadecimal addresses. Let's return to the history of the Acme Company. The company grew at a rapid pace and, needing more space, expanded into nearby buildings. Ethernet has strict rules about the length of a physical cable segment as well as the number of devices on the cable. So to accommodate this growth and add more computers and printers to the network, Acme Company used a network device called a repeater to extend the length of its Ethernet physical cable segment. A repeater is a physical layer device used to connect 2 or more separate physical cable segments together, making it act like one long cable. A repeater is a simple hardware device that regenerates electrical signals, sending all frames from one physical cable segment to another. Click the link on screen if you would like to learn more about rules governing the length of physical cable segments and the number of repeaters that can be deployed on a single LAN, or click the Continue button to continue with this topic. In a LAN using shared Ethernet access, any data sent over the wire must reach every part of the network or collision domain within a certain amount of time. For this reason, Ethernet physical cable segments or cable runs are limited in length and in the number of devices per run based on the amount of time it takes for a bit of information to go from one end of the wire to the other. Therefore, faster mediums, such as fiber, have longer length restrictions. The table on screen shows the maximum cable length for each type of Ethernet media. In the early 1980s, repeaters were used to extend the reach of Ethernet as well as to isolate failing cables. However, each repeater that the signal goes through adds a small amount of time to the length of the transmission. To ensure that timing limitations are not violated, the Ethernet standard implements the 5-4-3 rule for deploying physical cable segments and repeaters. This rule divides the network into two types of physical cable segments: populated or user cable segments and unpopulated or link cable segments. Link segments connect repeaters together and cannot contain end-user devices. So the 5-4-3 rule means that there can only be a total of 5 cable segments connected through 4 repeaters, and only 3 of the 5 segments can contain end-user devices. The other 2 segments or link segments are used to connect the repeaters. Note that the LAN shown on screen is still one collision domain. As we saw earlier, increasing the number of devices increases the number of collisions on the network and decreases the overall network performance. Exceeding the 5-4-3 rule would likely result in a network with too many collisions to be functional. Ethernet networks were originally implemented with coaxial cabling. With the introduction of the IEEE 10-base-T standard in the late 1980s, Ethernet networks started using twisted pair cabling. Click the link on screen if you would like to learn more about the 10-base-T standard, or click the Continue button to continue with this topic. Twisted pair cabling consists of twisted pairs of unshielded but insulated wires. It is also known as unshielded twisted pair or UTP cabling. The first 10-base-T networks used ordinary telephone cabling, which is a type of twisted pair cabling. In this type of cable, there are 4 twisted pairs of wires, 2 for transmitting data and another 2 for receiving data. At this time, a new device called a hub also became available, and Acme replaced their repeaters with hubs. Now, the physical topology or layout of their network changed from a shared bus to a star configuration. In Acme's old shared bus configuration, many devices were daisy-chained together using a single network cable, which meant that if the cable failed, or if one device on the cable was causing network trouble, every device on the cable could be impacted. In a star configuration, each device uses its own twisted pair cable to connect to a port on the hub. If a cable fails, it will impact only one device, and if one device is causing trouble on the network, that individual device can easily be unplugged. Like a repeater, a hub simply takes a signal that it receives from one connected device and passes it along or repeats it to all other connected devices. A hub is not an intelligent network device. It does not look at the MAC addresses or data in the Ethernet frame and does not perform any type of filtering or routing of the data. It is simply a junction that joins all the different devices together. Even though each device has its own cable connecting it to the hub, access to the network still operates by Csma CD, and collisions can occur on the shared bus inside the hub. Having twisted pair cabling and hubs simplified many networking operations for Acme, but as more time passed and Acme's network continued to grow, network performance still suffered and employees complained. Remember our discussion of the rules governing a group conversation? As more and more people join the group, it becomes more and more difficult to have an uninterrupted conversation or understand what everyone is saying. One way to fix this problem is to break the large group up into several smaller groups, which is how networks handle the same problem. Let's see how Acme divided up their network. The group of Ethernet devices that compete with each other for access, you might remember, is called a collision domain or network segment. A hub operates at layer 1 and makes both sides of the hub act like one very long physical cable, repeating each and every frame. As more and more computers are added to the network, more potential for collisions is created. To break their network up into smaller segments, Acme installed a network device called a bridge. Just like a repeater or a hub, a bridge connects two or more physical cable segments to create one larger network. Unlike a repeater or a hub, though, each side of the bridge becomes a separate collision domain or network segment. So a bridge can be used to break up a large network into separate collision domains. This process is often referred to as network segmentation. By breaking the large networks into smaller collision domains, the number of devices competing for network access declines, and of course the number of collisions also declines. If a collision does occur, the bridge isolates the collision to a single domain. A bridge operates at layer 2 and helps regulate traffic flow using MAC addresses. Let's see how this process works. On screen is a bridge with 3 ports. Each port is attached to a hub, and each hub is connected to 2 devices. The MAC address of each device is shown next to the device. Ethernet bridges have 3 basic functions: forwarding frames, learning MAC addresses, and controlling traffic. A bridge uses a MAC address table, which is like a database, to help control and limit traffic on a network. Because a bridge is a layer 2 device, it can examine the source MAC address of each received frame. A bridge can then record the source MAC address and the port on which it was received in its MAC address table. Let's see how MAC address tables are built and how they are used to improve overall network performance. When a bridge first powers on, the MAC address table is typically empty. When an end-user device sends out a frame, the bridge receives it and looks at the source MAC address. In the on-screen animation, the source address is now designated on the frame with the letters SA. If this MAC address is not in the MAC address table, the bridge adds it and associates it with the port on which it came in. Next, the bridge examines the destination MAC address. If the destination MAC address is not in its table, the bridge forwards the frame out all of its other ports. This action is also known as flooding. Because the bridge builds a table of addresses when they come in, the bridge eventually learns through which of its ports destination devices are located, so it doesn't have to flood each and every frame out all its ports. When the bridge receives a frame with a destination MAC address in its MAC address table, it can forward or drop it selectively, reducing overall network traffic. If the destination MAC address is in the MAC address table and resides on the same port where the frame arrived, the bridge simply drops the frame because the end-user device has already received it. It does not forward the frame to the other ports or segments, reducing overall network traffic. If the destination MAC address is in the MAC address table and is located off a different port, the bridge forwards the frame only on that port, again reducing overall network traffic. If the destination MAC address is a broadcast or multicast address, the bridge must always forward it out every other port. Because a bridge is just another device in the collision domain, it follows the same MAC protocol as every other device. It is important to note that bridges never change the destination or source MAC address. They simply look at the destination MAC address to make their decisions. Here's a chance to see how well you understand bridge functionality. The bridge has just received the frame shown on screen on port 2. What will it do now? Type into the MAC address table to make any necessary additions. Then select each action that the bridge will take. When you are finished, click Check Answer. Not quite. Try again. That's still not quite right, because source address 0001.0002.1234 is not yet in the MAC address table. The bridge will add it to the table as a device on port 2. The MAC address table uses source addresses, not destination addresses, to build its data. So, the destination address will not be added to the table. Because the destination address is not in the table, the MAC address table does not yet know that the destination device is on port 3. So it will forward the frame to port 1 and port 3 in case the destination device is on either of those ports. Bridges were huge advances in the development of Ethernet LANs, but they weren't perfect. Often bridge network segments were interconnected to create redundancy, so that if a failure occurred on one segment, data could be sent by another route. But when there are multiple paths in a bridged network, loops can form. When a bridge receives a frame, it updates its MAC address table with the source MAC address. If it doesn't have the destination MAC address in its table, it floods the frame out every other port. In this case, both bridge B and bridge C receive the frame and update their MAC address tables. Bridge B doesn't have the destination in its table, so it forwards the frame out all ports. Bridge C doesn't have the destination in its table either, so it also forwards the frame it received on port 1 out all ports. But now bridge C has the frame it just received on port 2, and bridge B has the frame it received on port 3. They both update their address tables accordingly, and then flood the data out all ports except the port on which the data was just received. Bridge A receives data on port 3 and port 2. If it received the data on port 3 first, it will update its MAC address table to show that port and again flood the data out all other ports. And then bridge A will update its MAC address table again to show that data arrived on port 2 and again flood the data out all other ports. As you can see, in this scenario, the address tables are constantly changing, and the simple bridge forwarding rules we just discussed have created a forwarding storm where the same frames are forwarded endlessly in a loop. Broadcast and multicast traffic can create the same issue. Remember that if the destination MAC address is a broadcast or multicast address, a bridge must always forward it out every other port. When a network has loops, bridges receive broadcast traffic and rebroadcast it out all ports again and again, creating what is known as a broadcast storm. A broadcast storm can block all other network traffic and bring a network to a complete standstill. We don't show it here, but as we saw in the previous scenario, each bridge must also keep updating its MAC address table each time it receives the same frame on a different port. To prevent loops, bridges used the Spanning Tree Protocol, or STP, which selectively disables bridge forwarding on individual ports to ensure that the network topology is loop-free. Discussion of the Spanning Tree Protocol is beyond the scope of this course. Now let's look at the devices used in today's networks. Network devices today look nothing like the repeaters, hubs, and bridges used just a few years ago. Instead of a group of devices sharing the bandwidth of a 10 megabit per second network, network devices today get dedicated bandwidth with speeds from 10 or 100 megabits per second up to 100 gigabits per second. That's an increase in speed of 10,000 times in just a few years. Click the link on screen if you'd like to get a better idea of the relative sizes of network speeds, or click the Continue button to continue with this topic. In this section, we'll see how new devices called switches and routers change networking configurations and dramatically increase network speeds. Let's recall what we learned about collision domains and half-duplex data transmission. As we learned in the last section, bridges break or segment one large network into smaller collision domains. Because fewer devices are competing for network access, overall network performance improves. However, older devices relied on half-duplex data transmission. That is, a device first had to listen before transmitting to ensure that the network was available. The device also assumed there were many other network devices on the same network segment and therefore had to be ready to deal with collisions. In half-duplex Ethernet networks, after a device transmits data, it listens to the network and expects to hear the same data in the exact same pattern. If the device hears a different pattern, it assumes a collision has taken place. If a device must wait its turn to send data and then cannot send and receive different data at the same time, time is wasted. Waiting and listening takes up valuable network time and makes the network not as efficient as it could be. As we'll see, modern network devices have greatly reduced the chances of collisions and, in doing so, greatly increased network performance. As we mentioned earlier, end-user devices today connect to network devices using twisted pair or fiber optic cables instead of coaxial cables. Twisted pair wiring offered new possibilities for networking that coaxial cable didn't have. When we take a closer look at the twisted pair wires used in an Ethernet environment, we see that there are a pair of wires for transmitting data and a separate pair of wires for receiving data. The pinouts shown on screen are for regular Ethernet end-user devices, such as PCs, servers, printers, and routers, a network device we'll discuss later. Click the link on screen if you'd like to learn more about the wiring for straight-through and crossover Ethernet cables, or click the Continue button to continue with this topic. Because there are two different paths, an Ethernet device is capable of transmitting data onto the network using the transmit pair while it continues to listen using the receive pair. So in theory, Ethernet networks were no longer restricted to half-duplex data transmission, but could transmit and receive simultaneously. In practice, however, it wouldn't work in a bridged network. In a bridged network, a network can be segmented only so far. Users still compete with each other for network access on the same segment or collision domain. As long as that was the case, collisions would still be a problem. It was still necessary to listen to make sure the line was clear before transmitting data, and after sending data, listen again to make sure a collision had not occurred. To overcome that limitation and take full advantage of twisted pair cabling, the switch was developed. Ethernet switches are similar to bridges in that they are both Layer 2 devices that help manage and control traffic. As with a bridge, each port on an Ethernet switch creates a separate collision domain. Just like a bridge, an Ethernet switch forwards traffic and learns which MAC addresses reside off each of its ports. Where they differ is that Ethernet switches have significantly more ports than do bridges. Today, a simple switch might have just a few ports, but an enterprise-level switch can have hundreds of ports. When a single Ethernet switch port can be dedicated to a single end-user device, hubs and bridges are no longer necessary. Because switches dedicate a single bridge port to one end-user device, collision domains have only two devices, the end-user device and the switch. End-user devices no longer compete with each other for network access, and with twisted pair cabling, each transmit pair is an isolated circuit. Because both sides of the connection will receive data from only a single network device, packets will not get corrupted by multiple stations transmitting simultaneously. By isolating each end-user device in its own collision domain and providing two separate paths to transmit data to the switch and receive it from the switch, collisions are effectively eliminated. Without the danger of collisions, devices can freely transmit and receive data at the same time, which is called full duplex data transmission. Full duplex data transmission is similar to using a telephone, where you can talk and listen at the same time. Ethernet switches with full duplex data transmission offer much greater bandwidth than bridges did. With full duplex data transmission and dedicated switch ports, an end-user device can send and receive data simultaneously, effectively doubling network performance. End-user devices no longer have to share 10 megabit per second or 100 megabit per second of bandwidth with other end-user devices. Finally, in addition to basic Ethernet connectivity, switches make possible virtual LANs or VLANs. VLANs provide a way to break a single LAN into separate LANs on the same switch. Earlier we learned that when a bridge receives a frame with a broadcast destination address, it must forward the frame out every other port. The same is true of switches. Segmenting a network with switches fixes the collision problem, but it doesn't address the fact that broadcast traffic must be sent out all other ports, which uses up precious network bandwidth. VLANs help solve this problem. Here you see a single switch with two different VLANs identified by color. Essentially, VLANs are a way to subdivide a LAN. A VLAN is a group of PCs, servers, and other network devices that may be connected to the same switch as other devices, but behave as if they are connected to the same smaller LAN or a completely separate switch. Devices that are in one VLAN do not receive broadcasts from devices in another VLAN. If a device on the purple VLAN sends a broadcast, the switch sends the broadcast out only the ports configured on the purple VLAN. The switch doesn't send the broadcast out the green ports, even though they are on the same physical switch. When devices on different VLANs need to communicate, even if they are on the same switch, a router must be used. We discuss routers in the next section. A more detailed discussion of VLANs is beyond the scope of this course. Switches do have limitations. Because they forward frames just like bridges, they're susceptible to the same sort of network hazards, such as loops, that bridges are. Both switches and bridges must forward broadcast and multicast frames out every port. If there are loops in the network, broadcast and multicast frames can cripple a network. Like bridges, switches also use the Spanning Tree Protocol, or STP, to prevent network loops. Likewise, switched Ethernet networks might not improve performance if a network has a lot of multicast and broadcast traffic. Finally, Ethernet switches might not be able to interconnect geographically dispersed networks. To solve these problems, a different network device called a router is required. Whereas Ethernet switches operate at Layer 2 and can examine only the destination Layer 2 or MAC address, routers operate at Layer 3 and can examine Layer 3 addresses. In our next section, we'll examine the difference between Layer 2 and Layer 3 addresses as well as router operation. We wouldn't be giving a true overview of today's Ethernet networks without discussing wireless LANs. As the name suggests, wireless LAN technology allows the extension of an Ethernet LAN segment without the need for cabling. You can think of a wireless LAN in much the same way as we have discussed a wired Ethernet LAN. The primary differences are the equipment. Instead of using an RJ45 NIC to connect to a switch, wireless clients use a wireless NIC, which has a radio built into the device, to connect either directly to a switch or through a wireless access point, which subsequently connects to a switch. Let's take a look at three common wireless LAN architectures: the autonomous architecture, the centralized architecture, and the distributed architecture. The first type of WLAN architecture, autonomous architecture, is known as FAT access point, or FAT AP architecture, where all functionality is coded into every access point, or wireless termination point. Home networks today often make use of the autonomous architecture in the form of a single FAT access point. The second type of WLAN architecture, centralized architecture, is known as a switched WLAN system. In this type of system, the access points become thin or lightweight, and there is a central switch or access point controller that actually manages them. Most enterprise networks today choose this centralized or switched WLAN model. The primary reason for this is scalability. The autonomous WLAN architecture is impractical in an enterprise setting. In an enterprise setting, you may well require hundreds or even thousands of access points, and if each one must be managed individually, it quickly becomes unworkable. With a centralized or switched WLAN system, the access point controllers are the managed devices. This reduces the management problem by at least a factor of 10. Switched WLAN systems are physically more secure than other architectures. The access point controller may be installed in a locked data closet or data center, and the thin access points are a less likely target for theft, as, without the controller, they can't be used. In addition to this, these access points typically don't store any configuration data or admin user credentials. The access point controller can also include a powerful network processor that can provide value-added functionality, such as security and access control, VLAN management and manipulation, user roaming between access points, and quality of service. The third form of WLAN architecture is distributed architecture, also known as a wireless mesh. A wireless mesh can be used to create a dynamic network in environments where cabling would be impossible. For instance, this type of network is used by U.S. military forces in field operations. In a wireless mesh network, data is repeated over wireless to neighbor nodes, not all of which are connected to the wired network. Like a network of routers, the devices make forwarding decisions to get the data through the network as efficiently as possible. Now let's look at the standards that enable wireless LANs. Wireless LAN technology dates back to the 1970s. However, widespread use of wireless LAN technology was prompted by the adoption of IEEE 802.11 standards in the late 1990s. In addition to the original standard, many extensions have been added over the years. We can refer to them collectively as the 802.11 group of standards. The 802.11 group is actually only responsible for standards at Layer 1, the physical layer, and a part of Layer 2 called the Media Access Control sublayer. At the physical layer, the 802.11 group of standards defines a variety of different connection types for wireless links of up to 100 meters for indoor connections or 500 meters for outdoors. The original standard, released in 1997, defined a physical layer operating at a frequency of 2.4 gigahertz with speeds of 1 and 2 megabits per second. The 802.11b extension to the standard allowed higher wireless speeds of 5.5 and 11 megabits per second operating in the 2.4 gigahertz band. This specification was the first to be marketed as Wi-Fi, and it gained widespread use. A common problem for 802.11b wireless, as well as the original standard, was interference from microwave ovens, cordless phones, and other devices operating in the 2.4 gigahertz range. Frequency hopping spread spectrum, or FHSS, and direct sequence spread spectrum, or DSSS, modulation were used by these standards to control interference. The 1999 802.11a and the 2003 802.11g standards increased wireless speeds to 54 megabits per second at 2.4 gigahertz and at 5 gigahertz frequencies. The new OFDM modulation technique also further reduced issues with interference and increased the stability of wireless connections. In 2009, the 802.11n standard introduced a multi-input, multi-output physical layer, which uses multiple wireless signals to greatly increase the amount of bandwidth that can be transmitted simultaneously. 802.11n has the potential to take connection speeds up to around 600 megabits per second. The 802.11ac standard, which is expected to be finalized in 2014, is expected to allow wireless connection speeds of 1 gigabit per second. The standards at Layer 2 primarily control who may use the wireless channel at any point in time. The primary access method is Carrier Sense Multiple Access Collision Avoidance, or CSMA-CA. A wireless client cannot detect collisions while it is transmitting, so it relies on receiving positive acknowledgments from the access point to confirm that data was received. This is slightly different from CSMA-CD, which we saw in a wired example earlier. CSMA-CD relies on detecting collisions when they occur. Let's see how CSMA-CA works. As we saw in the wired example, the client first listens to determine whether anyone else is transmitting. Each network device can either transmit data or receive data, but not both simultaneously. Only a single client can actually transmit at any one time, so if someone else is already transmitting, a client will wait to send data. Data transfer is always asynchronous, and acknowledgments are used to confirm the delivery of a frame. If the client does not receive an acknowledgment, it will back off and then retransmit the data. In addition to CSMA-CA, there is also an option with 802.11 to do virtual collision detection by using request to send and clear to send messages. In this case, the client must receive a clear to send message before sending data. This message is broadcast to all clients in range. We'll look at how this virtual collision detection system works in a little more depth later in this section. 802.11 also defines the option to use a centralized access method that requires an access point to poll all of the connected clients on a regular schedule to see if they have any traffic to send. In this situation, the client sends data when polled, if it has data to send. In addition to CSMA-CA, virtual collision detection, and asynchronous data transfers, other important specifications at this layer control security, so access control, authentication and encryption, roaming between access points, power save specifications, and quality of service. The generic 802.11 frame format is shown on screen. As you can see, it's longer than the Ethernet 2 frame. As we saw earlier, before the start of every Ethernet 2 frame, there is a preamble, which is used by communicating devices to determine the beginning of a new frame. 802.11n introduced an even shorter preamble called a Greenfield Preamble. In an environment that has no legacy devices, using the shorter Greenfield Preamble can increase throughput. However, at present, Most 802.11 end devices operate in mixed environments with legacy devices. This means that they must send both the Greenfield Preamble and the Legacy Preamble so that all clients on the wireless network understand that someone is about to transmit data. Take a moment to explore the other fields in the 802.11 frame. Move your mouse over each field to learn more. Click Continue when you are ready to move on. As we mentioned a moment ago, the frame control field conveys, among other things, the type of 802.11 frame. There are three main types of 802.11 frames: data, control, and management. Data frames include regular data that is being transmitted and certain types of special messages intended for the access point. Control frames are things like request to send, clear to send, and acknowledgement frames. Management frames include things like beacons sent by access points to advertise the wireless network or probes sent by a client looking for a particular wireless network. If you would like to learn more about the different types of 802.11 frames, click the link on screen. Click Continue to move on. Here are some common types of data, control, and management frames in 802.11. Let's discuss how a client finds and associates to an access point in a Wlan. First, the client must find an access point to connect to. A client may locate an access point passively by just listening for access point beacons. Or, this may occur actively by probing for a particular network. Any access point on the specified network will respond if it is available for connections. If multiple access points on the same network respond, the client will typically choose the one with the strongest signal. The client then sends an association management frame to the access point. The access point responds with an association ID, accepting the association. The client is then on the network and may send data. If the client must roam to another access point, it will send a reassociation request. For the client to roam successfully within the network, the new access point must respond with a new association ID. If the client had incoming data queued for it in the old access point, the data may be forwarded across the distribution system to the new access point and then delivered to the client. Just like in a wired Ethernet environment, once a client is connected to a wireless network and ready to send data on the wireless segment, traffic is subject to collisions. In the wireless LAN environment, the hidden node problem can cause collisions. This problem can occur when there are two clients on either side of an access point, which are within range of the access point, but which can't actually hear each other's transmissions. In this situation, both clients may listen to the channel, hear no data, and believe the channel to be clear. They then simultaneously transmit data. This causes collisions at the access point, which is unable to interpret either signal. In busy wireless environments with widely dispersed client devices, collisions such as this may cause bandwidth to drop as much as 40%. Neither client will receive an acknowledgement. Both must back off by a random interval and try their transmissions again. Wireless LANs have a couple of methods to help in these situations. First is the standard Csma-Ca method you've seen here. The other method available in 802.11 is virtual collision detection, which requires the use of the request to send, RTS, and clear to send, CTS control frames. Wireless networks can be configured to use this method for frames that are larger than a certain threshold. The client first listens to determine if the channel is clear. If it is clear, it sends a request to send and specifies the duration it expects to require to send its data. Every client that hears this frame will know that it has to wait before attempting to access the channel itself. The access point responds with a clear to send, confirming the duration value. This solves the hidden node problem, because even if Client 2 can't hear Client 1, it will receive the broadcast from the access point. Client 2 will not send data for the specified period of time. After the specified time period, the channel is available again on a first-come, first-served basis, and Client 2 can now send its data. Some bandwidth is lost to overhead traffic by using request to send and clear to send frames. However, the pros of using this mechanism outweigh the cons in dense user environments. As we've seen, to ensure the reliable delivery of data across a wireless channel under normal circumstances, every frame or fragment is positively acknowledged. If the acknowledgement is not received, the frame or fragment is retransmitted. There are a number of frame control settings that can have an impact on the reliability of connections. The Rts Threshold can be used to specify a size of frame above which the request to send, clear to send mechanism must be used. Retry counters specify how many times a device should try resending a frame before discarding it. A different value can be set for frames smaller or larger than the Rts threshold. The Fragmentation Threshold specifies what size of packet should be split into fragments, and the fragment lifetime specifies how long fragments should be kept while waiting for related fragments to arrive. There is a lot more to wireless LANs, including coverage, security, sensitivity, capacity, and other planning aspects, but these are beyond the scope of this course. For more detailed information, view the Wlan Fundamentals e-learning by clicking the link on the screen.